The last topic I wanted to cover in Chapter 12, and this will actually conclude our coverage of statistics. We'll be moving into linear algebra next. Right now I plan to actually have an exam on Monday. I was thinking about actually postponing exams until we got back to face-to-face instruction, but I'm afraid that may be longer than maybe initially anticipated. So I plan right now to do some sort of Facebook exam on Monday. I'll give you more details on that on Friday. But the last topic I wanted to cover here, the last topic for the exam, is for these bivariate data sets where we have both X and Y data, is estimating the standard deviation of the data. So again, in this section, there are several formulas aren't necessarily all that complicated, but for larger data sets, they can certainly take a while to compute, and that's why it's so convenient to use a computer tool like Octave or some other data analysis tool to do these calculations. But a couple definitions for a given data point xi. The predicted values of yi are given by, we just plug our xi data into our regression line formula to get values for yi. So these would be points on our regression line. Okay. The residuals are defined as being the difference between our actual yi values and our predicted values. This is actually the negative of the error terms that we defined previously, and corresponding to the residuals, we define what's known as the error sum of squares. So this is the sum of the squared residuals. And using the notation from the textbook, this is SSE, and the formula for SSE is it's the sum of, again, just the differences between the yi and the values lying on our regression line. And then using this, we can come up with an estimate for the variance of our data, which is also denoted S squared, and it's actually the sum of the squares, the error sum of squares divided by n minus 2. Computation formula for SSE, certainly you can use this formula, but for laying the data out in a table, it's a little more convenient to use this formula. SSE is equal to the sum of the yi squared minus beta 0. This is our intercept coefficient times the sum of the yi minus beta 1, which is our slope coefficient, times the cross product term. So in some of the homework, instead of giving you all the data in the homework problems, they'll actually give you the sum of the squares or the sum of the cross terms, so you don't have to go through all of these different calculations. Finally, to get to the last thing I want to cover here is the coefficient of determination, and that's related to the total sum of squares, or SST, and the SST is Alternate notation for it would be SYY, and it's just, again, the sum of yi minus the average y value. So this is an estimate for just the variance of the y. The residuals are the distance from the yi values to the points on the line. This is the distance from the yi values to the overall mean. And so this is the total sum of squares. Computation formula is the sum of yi squared minus the sum of yi squared divided by n. Okay, and it finally leads us to the coefficient of determination. Let me clean that up a bit. Whoops, went back a little too far. Determination. Notation for this is r squared, and it's actually just 1 minus SSE divided by SST. So the coefficient of determination will be a value that is between 0 and 1. The closer it is to 1, the better the data fits to a linear regression model. If r squared is close to 0, then this linear regression model is actually not a good fit to the data, which indicates that the data may be unrelated, or actually that it may have a nonlinear relationship instead of a linear relationship. The final thing I wanted to look at here is just now one final example, and mainly I wanted to show you how you can calculate all these terms using Octave. This is example 12.9 from your textbook. This is on page 486. So this actually uses the data from example 12.4, but I wanted to show you how to do the calculations in Octave. So here in this first line, again, we read in our data set. X is the first column out of this data matrix, Y is the second column, and I can compute my regression line coefficients. B1 is the slope, that's the covariance of X and Y divided by the variance of X, and then B0 is my intercept, that's the mean value of Y minus B1 times the mean value of X. And then to compute the SSE term, I can use the sum of squares function to get the sum of the squares of Y minus B0 times the sum of Y minus B1 times the sum of X dot asterisk Y. So the dot asterisk here in Octave or MATLAB, it means do an element by element multiplication. So these two vectors are of the same length. So this X dot asterisk Y will result in a vector whose elements are the products of the individual terms. Without the dot, Octave, MATLAB actually tries to do a matrix multiplication. That's not what I want here. That will be what we'll be taking a look at in when we get to linear algebra, but right now I'm interested in the element by element multiplication. So you can compare this formula to the formula I gave you during the lecture and see that it's kind of a direct translation from the mathematical notation into Octave notation. And so here's the estimate for the variance. It's the SSE divided by n minus 2, and again n I get is just the length of Y, and then similarly SST is the sum of the squares of the elements in the Y vector minus the sum of the Y the sum of the y terms squared divided by the length of y, and finally I can get the coefficient of determination. So if I run this, I have Octave actually prints out all the values. Again, the slope, the y-intercept, the error sum of squares. This would be an estimate of the variance. Square root of that would be a corresponding estimate of the standard deviation. Here's the SST term, and then finally the R squared term. It turns out to be about 0.8 here, which indicates that a linear fit is actually a pretty good fit to the data in this case.